Rohini College of Engineering and Technology. I am Vetrivel, Associate Professor, Department of Physics, Rohini College of Engineering and Technology. In this video, we are going to discuss about the domain theory of ferromagnetism, which is in the material science 4th unit, PH 8251. Course outcome. Upon completion of this course, the students will be able to understand the domain theory of ferromagnetism. The domain theory of ferromagnetism was proposed by Weiss in 1907. Actually, it explains the hysteresis and the properties of ferromagnetic materials such as iron. The ferromagnetic domains are small regions in ferromagnetic materials within which all the magnetic dipoles are aligned parallel to each other. So when we consider the ferromagnetic material such as iron, it consists a large number of small regions. They are called as domains. In each domain, the magnetic dipoles are present. In this picture, we can see how the ferromagnetic domains are present inside the material. In this picture, figure A represents the various ferromagnetic domains inside the ferromagnetic material. So here we see the ferromagnetic material is divided into a number of ferromagnetic domains with a small volume. In each and every ferromagnetic domain, a number of magnetic dipoles will be present, but without applying the external magnetic field, all the magnetic dipoles are randomly rotated in different directions. But when we see the second figure, when the external magnetic field B0 is applied, all the ferromagnetic domains will be rotated so that the magnetic dipoles present inside the material will be aligned with respect to the direction of the applied external magnetic field. So this figure clearly indicates that the magnetic dipoles will be aligned in the direction of the external magnetic field. Now let us see what are these ferromagnetic dipoles. So what is the importance of these ferromagnetic dipoles? So ferromagnetic dipoles are nothing but the small tiny magnet. They are confined within the ferromagnetic domains. These ferromagnetic dipoles have the property of the magnets. They have the north pole and south pole. Each and every magnetic dipole will behave as the magnet. If a material has a large number of magnetic dipoles, the magnetic behavior of the material will also be more. We can see the ferromagnetic materials such as iron will be easily magnetized. That means the iron will be easily converted into the magnet. So what is the reason behind it? What is the concept behind it? That is explained by this ferromagnetic domain theory. When we apply the external magnetic field, all the ferromagnetic dipoles will be aligned in a particular direction so that the material will be easily magnetized. Now let us see the postulates of domain theory. The first point, a ferromagnetic material is divided into a large number of small regions called domains. Each domain consists the magnetic dipoles. Each and every magnetic domain is separated by a small wall. It is called as the domain boundary or domain wall. Third point, in the absence of external magnetic field, all the magnetic dipoles are in different direction so that the net magnetization of the material is 0. Fourth point, when the external magnetic field is applied, all the magnetic dipoles are aligned in the same direction of the applied external magnetic field. Fifth point, all the magnetic dipoles will be aligned due to the following process. We have the question that how all the magnetic dipoles will be aligned in the same direction. So that will happen by the two following processes. The first process by the motion of the domain walls, and the second process by the rotation of the domains. So the first point, by the motion of the domain walls. When a small amount of magnetic field is applied, the dipoles in the domains are aligned parallel to the applied magnetic field. It increases domain area by the motion of the domain walls. Here we see when the external magnetic field is applied, the domain walls will be moving from one place to another place. As a result, the volume of the domain will be increased. That means 3 or 4 or whatever the number of maybe, the small magnetic domains will be converted into a single magnetic domain, so that all the magnetic dipoles will be aligned inside the ferromagnetic domain in the same direction. Now let us see the second point. When this process is over, that means when all the ferromagnetic domain walls are displaced, now the ferromagnetic domain starts to rotate itself. As a result, when the ferromagnetic domain starts rotate itself, all the magnetic dipoles present inside the domain also rotate, so that they will be aligned in the direction of the applied external magnetic field. Here we see this picture clearly shows that the movement of domain walls and also the rotation of the domains. See in the first figure, here it is a ferromagnetic material. In this picture, the ferromagnetic material is divided into 4 ferromagnetic domains. Each domain has a ferromagnetic dipole. So without applying the external magnetic field, that is H is equal to 0, all the magnetic dipoles are aligned in a random direction. Now let us move to the second figure. Here, when a small quantity of external magnetic field is applied, that is indicated here, H is small, H is not equal to 0. So a small weak magnetic field is applied, so that the ferromagnetic domain walls are moving from one place to another place, so that the volume of the ferromagnetic domains are also increased. Now let us see the third figure. Here also H is not equal to 0 because H is large. That means a strong external magnetic field is applied. The ferromagnetic domain wall further displaced from their original position, so that the volume of the single domain increases rapidly. As a result, all the ferromagnetic dipoles present inside the material will be aligned. After this process is over, now the ferromagnetic domain starts rotating itself, so that all the magnetic dipoles present in the ferromagnetic domain will be aligned in the same direction of the external magnetic field. Here H represents the external magnetic field. Now let us see the figure. The first figure, the situation or the condition of the magnetic dipoles inside the ferromagnetic domain without the application of the external magnetic field. Here we can clearly see that all the magnetic dipoles are aligned in the random direction. There is no perfect order at all. Now let us see the second figure. When we apply the external magnetic field, all the magnetic dipoles present inside the ferromagnetic domain will be aligned in the same direction. That means, suppose when we apply the external magnetic field in the x-axis, all the ferromagnetic dipoles are also aligned in the same direction, that is along the x-axis. When all such dipoles are aligned in the same direction, the material will be easily magnetized. That is, the ferromagnetic will be easily converted into the magnet. This is a basic concept of the domain theory of ferromagnetism. So, in this video, we have clearly seen that the concept of ferromagnetic domain theory for the magnetization process of the ferromagnetic material such as iron. Thank you.